slow it down.
Right. Are you understanding the question? No.
Yeah.
Between the mass, the big mass M and the ground is smooth. Okay, and there is friction between the other masses M1 and M and M2 on the ground.
Yeah.
There is friction between M2 and the ground because M2 is rough. Okay, but capital M is smooth. What is done? Draw the free body diagram of capital mass M.
Yeah.
Okay, is it matching with what I have drawn?
Yeah.
And don't forget this friction force F1. Right, that friction force is there towards left. The direction of friction force F1, it can change depending on whether it is slipping between M1 and capital M. By understanding that point,
Yeah.
okay, suppose this is the friction force acting on the capital mass M. So even when there is slipping, the above one will try to act in the left only. Bhavya, got it?
Yeah.
This friction force acting on the capital mass M. So even if F is large and there is slipping between M1 and capital M, this friction force will try to act towards left. Okay, even if I assume the direction of friction F1 wrongly, when you solve the equations, you will get the value of F1 as negative. Okay.
Okay.
So in that case, you just have to reverse the direction of F1. Okay, the first part is done. No. What about the next one? Magnitude of friction force between M1 and F1. Okay, you have to solve for these three. And this is the condition that you are given. Okay, so you have to draw the two free body diagrams or the other two blocks, M1 and M2.
Okay, sir.
And the direction of F1 should be consistent with what you have drawn for capital M. Capital M, the friction force acting on the left, so this will compensate that one. Newton's third law is the interaction force, no? So F1 on small mass M1 will be towards right. Is the free body diagram correct? M1 and
Yeah.
M2. Okay. Now another important thing that's missing in the free body diagram is what? Directional acceleration, right? Free body diagram also, it shows the forces, but you should also know where the acceleration is. Because the net force should be equal to m into a. Here it is not at rest, it is moving. Okay, so you have to assume the direction of acceleration. Right, so the complete diagram will be like this. The big mass m is moving towards right with acceleration a, and if there is no slippage between m1 and the big mass, then the acceleration of m1 will also a. Okay, I am taking this case 1, no slippage between M1 and capital M. Okay, and there is slippage between M2 and ground. And the chances of this case being correct is more because the friction force F1 is twice of F2. Okay, so the chances of M1 not slipping with M2 slipping is more. Okay, if the assumption is wrong, then we get the wrong answer, so it's a contradiction. So we'll say this case is not valid. But this is a more likely case because the friction force F1 is twice of F2. So the chances of M1 slipping on M is less. Got it? Bhavya?
Yes, sir.
Okay.
Yes, sir.
So I've taken this particular case 1, where there is no slippage between M1 and capital M, but there is slippage between M2 and ground. When there is no slippage between M1 and this big mass, and the big mass is moving towards right, definitely M2 also has to move. Once M2 is moving, there has to be a slippage between M2 and the ground. Without M2 not slipping, it's not possible, because the string length is constant. Okay, since M1 is moving, M2 has to move with respect to the ground. So there should be slippage between M2 and the ground. Is it clear?
Yeah.
Okay. So that is the case I've taken. And in that situation, since there is no slippage between capital M and the M1, the acceleration of M and M1 are same. Okay. And the string length is constant, right? So if M1 moves towards right by distance x, M2 will move with the same distance x. Because the string is tight. Okay. So the acceleration of M1 should be same as M2, as long as the string is tight. And acceleration of capital M and M1 are same because there is no slipping. Got it?
Yeah.
Okay. Since the string is tight, when M1 moves by a distance x, M2 should also move with the same distance x. Okay, and acceleration of M1 is twice the derivative of x1. Okay, so once the displacements are same, acceleration will be same. Okay, that's why all the three have the same acceleration A towards right in this particular case 1. Okay, once you have this thing, you just have to write the equation. Then it's trivial. This is the important step. Okay, after that you will get these three equations: 1, 2, 2, and 3. Okay, this is the horizontal force equations. Here the horizontal force is F1 minus T. So F1 minus T is M1 into A. Okay, M2 it's T minus F2. So T minus F2 is M2A. Okay, and then this one, these things will cancel. Tension and in the horizontal direction will cancel. Okay, the only force in the horizontal direction is F and then F1. So F minus F1 should be capital M into A. Right? And he has given the condition that F1 equal to 2F2. So now we have to solve these equations. How many unknowns are there? F1, F2, capital F, and A. 4 unknowns, right? Unknowns are F1, F2, capital F, and then the acceleration E. And how many equations are there? This is the fourth one. This is the fourth equation. Okay, so 4 equations and 4 unknowns, so it is solvable. And there should be an easy way to solve it, because IIT JEE question calculations won't be difficult. Only the conceptual clarity is required.
Yeah.
So 1 and 2 equation, if I add them, tension will go, only acceleration will remain. 1 and 2 equations, if I add them, tension will go away. So only acceleration is unknown. Before that, one more thing is there. You can calculate F2. F2 is, see, since there is slippage between the mass M2 and the ground, F2 is the maximum friction force, which is equal to mu to N. Okay, F1 is not mu to N because F1 it did not be maximum. The friction force will be maximum when there is a when it has started moving. Friction force is variable force. Okay, but when it is started moving, then the friction force is maximum friction force. Here there is motion of M2 relative to the contact surface. So F2 is mu into N2, but F1 need not be mu into N1. It will be different. So F2 is known. F2 is mu into N2, which is M2 into G. So F2 is 15 Newton. Is that clear?
Yeah, sir.
Okay. And this he has given this relation F1 equal to twice F2. So from that we'll get F1 as 30 Newton. Okay. So since F1 and F2 are known, this is actually two unknowns, capital F and A. These two are known now. So two unknowns, capital F and A, and we have three equations. So we can solve them. So 1 and 2 will get acceleration as 3 by 5. Acceleration value is correct?
Yeah. Yes, sir. I think so.
Okay. And after that you have to find capital F. That you can get from this one. And capital T you can get from this one.
I think capital F is okay. Yeah, capital F is 60 already.
Bhavya, getting it?
Yeah.
Acceleration value you got, no?
Yeah.
And from equation 3 you can get the value of capital F.
Yes, sir.
And from equation 1 you can get the value of tension. You can also use equation 2, both are same. So you can use 1 or 2. I have used 1. So all the values are in
Yes,
SI
sir.
units. SI units. So acceleration is 3 by 4 meter per second square. Tension is 18 Newton. So yeah, it's a subjective question. So these are the correct answers. This one. And he has drawn a free body diagram like this. He has put the pulley here. Right? With the direction of friction. Is it clear?
Yeah.
Okay. So the important thing is we are assuming this particular case. There is no slippage between M1 and capital M. And there has to be slippage between M2 and M because the string length is constant. When there is no slippage between M1 and M and it's moving, there has to be slippage between M2 and the ground. Okay, so with this case, we have got the answers. So we know once we get the answer, this is the one that's happening. Because if this is not happening, then you will not get the correct, sensible answer. There will be some contradiction. Okay, so in other cases, there is slippage between M1 and capital M. Okay, and this capital M is moving towards the right. In that case, the acceleration of capital M will be say A, and the acceleration of M1 will be say A1. Okay, but since the string is tight, the acceleration of M2 will also be A1. In that case, the acceleration of M1 and M2 will be A2, sorry A1, and the acceleration of capital M will be E. Getting it?
Yes.
Yeah. Okay. And in that case, when the slippage is there, so this capital F1 will be maximum friction force. There will be mu N1. Okay. And here also there will be here there may be slippage or may not be slippage. This can be stationary in the sense that the value of A1 might be 0. That's possible, no?
Yeah.
The A1 M1 may be stationary with respect to the ground, so that way A1 will be 0 and A2 is also 0. Actually, A2 is same as A1 because of the string. Okay, in that case, when you work out, the tension in the string should be equal to F1. I mean, related to mu F1. And if you use that value of tension here, you will find out that there will be slippage between M2 and the ground. So there is a contradiction. So that case will be ruled out. Okay, but since he has given this condition that F1 is twice F2, the case one which you assume is the most likely thing that to happen. And once you assume this case and got a sensible answer, you know this is the thing that's happened. So conceptual clarity is required here. Another thing is the value of the friction force is mu into n only when there is slipping relative motion. This F1 is not mu into n1 because there is no relative motion between m1 and the capital. So the friction force will not be maximum here. This is the catch here. Okay. This is IIT 2000 question. So is it clear?
Yes, sir.
Yeah.
Right. This question is a bit on the difficult side because it time consuming and the conceptual clarity is required, and there are more than one cases, and if you don't choose the case one as the right one, then it will take some more time. So it is little bit on the difficult side. Okay, right. Let me finish with one basic concept. See, if there is a string here, and I'm pulling with a force F, what is the tension in the string? Bhavya?
Yes, sir.
This is a string, and one end I'm pulling
Yeah.
with force F. So what is the tension in the string?
F.
What about Daksh?
T plus F.
Okay. Now I have a fixed support. Okay, the same string. I'm pulling the force F. So what will be the tension now?
F.
What about the first case? Tension?
Sir, it should be attached to a rigid object. You're saying
No,
like that.
it is not.
So, sir, it will be 0, right?
Yeah. In the first case, tension is 0 because there is nothing to stop it. So it will be like a free falling body. Okay. The tension is
Okay.
0. Okay. Now we have another string. Same string, but different case. I'm pulling this side with the force F and this side with the force F. So what is the tension now?
0. No, 2F, sorry.
Daksh?
2F.
Tension
2F.
is F. Tension is F.
Sir, how?
See, you'll create a tension in the string only if you pull both the sides with equal force. Okay. If the forces are
Okay.
not balanced, the string will start translating in addition to tension. So to create a tension, T in a string, you have to pull both the ends of the string by tension force T equal to T. Okay. So if I'm pulling the string by here, the pulling force is given by the support. There's the resistance of the support is actually creating the pulling forces. Suppose if I have to draw a free body diagram of this string, I'll take the string and then replace this contact by a force F, or contact force is T, and here the force is F, so T equal to F. Okay.
Yeah.
So this is for a string. Now I take a spring and pull one end of this spring with the force F. What is the tension here?
0.
0. Yeah. But suppose if it is connected to a support, the tension is
Okay.
Yeah.
Oh, F, yeah, F.
F. Right. Okay, fine. Now this is the support. Okay, one more thing. Right, I'm put. Now same thing. Spring. Now I'm pushing with the force up F. So what is the tension now?
Two F.
Bhavya?
Sir, 2F.
No, tension is F only. The only thing is here is the spring is getting stretched and here it is getting compressed. The spring force is always K into X, where X is the change in the length. So X if X is an elongation, the force is same. If X is a compression, then also the force is same. Only the direction of the tension force will be different. Here the direction of the tension, first case the direction of tension force is to compress the spring. In the second, the direction of the tension force is to bring the spring back to its original position. Okay. Now I have a say this is a string. Okay, and then I'm applying a pulling force. F. Now what is the tension in the spring? See here I've directly connected spring to the
F
rigid surface. Now I
by
pushed a string connected to the
S by
spring.
2. F by 2.
Don't make random guess.
Sir, F only.
Yeah. Now this same thing, the rigid support, string, and then spring. Then I'm applying a force in the upward direction. Now what is the tension here? This is a string.
F.
Sir, F only. Because the string will
When you try to push it, the string will slack.
sir, but when it reaches the rigid surface.
No, not. I'm not going to that extent. Before reaching that rigid surface, the string will be slack. So there is, yeah. So on the spring, one side there is a force F, the other side it's free. So we just start moving without any change in the length of the spring. Okay.
Yeah.
Now instead of string, I have a rod, and then this spring. Okay, and then I try to push it up. And then I apply a upward force. This is the rigid surface. In that case, what is the tension?
F.
Yeah. Okay, fine. Just revise these things and then get it clear.
Yeah. Okay,
Fine.
sir.
Okay. We'll meet tomorrow,
Okay, sir.
11:30.
Okay, sir.
Okay.
Bye, sir.
Check your notes.
Yeah.
Bye.
Yeah. Bye. Thank you, sir.